Thanks, Chado. Hi everyone, it is my pleasure today to introduce our speaker, who is Qinghua Liu. Qinghua is a third-year PhD student at Princeton University, advised by Qingjin. His interests cover reinforced learning and multi-agent, among others. Qinghua has done awesome work recently in reinforced learning. For example, you may recall the talk on under complete PONDPs. Today is going to talk about the exploration with function approximation, focusing on a new complexity measure called Bellman Eluder Dimension. With this, Qinghua, the floor is yours.
Oh, thanks. Thanks, Matthew, for the kind introduction. And thanks for inviting me again to this great seminar. So I'm Qinghua. As introduced, I'm a PhD student at Princeton working with Chi. So today I'm going to talk about our recent work on Bellman Eluder Dimension, where I will talk about two things as this title suggests. So one is about the new rich classes or reinforcement problems. We will see this class is really rich, which kind of contains all the existing known tractable problems. And the second thing is we will have some general sample efficient algorithms to solve this general reinforcement learning class. So this is a joint work with my advisor Chi and my lab mate Sobhan. I will first do an overview of this work, including the background and our results at a high level. And then I will go over the details about what is the concrete definition of the Bellman Eluder Dimension and what are the results we can obtain. So first, as most of you know about reinforcement learning, so it's a framework trying to solve some sequential decision problems. So in the real world, there are a lot of such problems, like when you play Go, or when you design robotics, or when you program autonomous driving cars, or even when you play poker. So basically everything where you need to make a sequence of decisions based on the previous feedback can be formulated into this framework. And also recent years, there are a lot of very impressive empirical results in this field. Basically, they solve these problems using deep reinforcement learning and achieve some superhuman performance. So when we want to talk more about understanding reinforcement learning, usually we model it as a Markov decision process. So here I will just introduce it from a high level. So let's take this robot folding towel as an example. The Markov decision process involves both the agent, this robot, and the environment. They are interacting with each other. So in this robot example, we have states, which is like the position and the angle of its arms, and also the position and the shape of this towel. The agent, this robot, can take some action, like move or rotate its arms, which will have an effect on the environment, like changing the position and shape of this towel. And eventually, the environment will return reward 1 if the robot successfully folds this towel, and reward 0 if it fails. And the goal of reinforcement learning is to find the best policy that maximizes the cumulative reward. In this application, the best policy is basically the best way to move its arms so that we can fold this towel as fast and accurately as possible. And to achieve this goal, many classical reinforcement learning schemes claim that the best policy can be found if they are given infinite amount of samples and infinite amount of computation times. But in practice, we never have an infinite amount of resources. So efficiency is really important. When we talk about efficiency, there are two types of efficiency. One is sample efficiency. That is, we want to use as few samples as possible. Because in practice, collecting samples can be really expensive and time consuming. So for example, like in autonomous driving, collecting one trajectory probably takes 10 minutes. And also if we crash the car, it would be even more expensive because we may need to buy a new car or repair the car. And also, we care about the computational efficiency, because in practice, the reinforcement learning models are typically very large. So training a deep learning model can take weeks or even months. Let's take the famous AlphaGo 0 as an example. The paper says the model is trained using 10 to the 7 games, and one pass of the entire training set takes more than 1 month. So as a result, there is a strong practical motivation for us to study the efficiency of reinforcement learning from a theoretical perspective. So what do we know in theory about those sample efficient or computationally efficient algorithms? It turns out a lot of classical reinforcement learning results have been focusing on the so-called tabular case, which is like this board game. So the special property of this tabular setting is the number of states and actions are typically finite and oftentimes relatively small. So the strategy for solving this tabular case is very simple. Basically, we just try to visit all the reachable states and learn the transition dynamics at those states to a reasonable accuracy. And there have been abundant results for this tabular setting. We know what the minimax sample capacity is for this setting, and we have multiple algorithms that can achieve this minimax rate. For example, the value iteration algorithm with upper confidence bound by Azar et al. In 2017. One important thing about this tabular setting is the minimax sample capacity scales linearly with the number of states. And the reason is very simple, because in the tabular setting, we don't know how to generalize knowledge between different states. But however, in practice, this is not the case. For example, in this StarCraft game, if you count the number of different states, it will be like 10 to the hundreds. So you can never expect to visit all of these states repeatedly. And in fact, most of the states will not be visited even once throughout the entire training process. So to solve this kind of large-scale IO problem, we need to adopt a different strategy called function approximation. We approximate either the value function or the policy by some functions in a parametric function class. So for example, we can choose this F to be linear function class or deep neural networks. And of course, doing this function approximation introduces a lot of new challenges. And the first is, as we said, most of the states are not visited even once. So we want to have a mechanism so that we can generalize knowledge from the visited states to the unvisited states. And also, because we assume we have some function class, so our expressiveness is limited. The function class we pick definitely should not include all functions over the city action space. So we might encounter some technical problems, like in the intermediate steps, when we compute some function, but it's outside this function class. So we need to either project it back, or we need to introduce some approximation error. And this will make the analysis very complicated. And finally, because we are doing reinforcement learning, so we always need to deal with this exploration versus exploitation trade-off. And this is already not simple in the tabular setting. And by doing function approximation, we just make it even harder. So feel free to interrupt me if you have any questions, because I need to switch the window to see the chats. Okay. And due to all these complicated challenges, most of the existing theories about function approximation are only able to do some special cases, like linear MDPs or linear quadratic regulators. There are very special cases with very strong assumptions. This is basically what we have so far for reinforcement learning. But if you think back about supervised learning, which is something we have been studying for decades, we have all kinds of results far beyond the linear setting. We can say as long as the function class has some low complexity measure, for example, low VC dimension, or low Rademacher complexity, or low little stone dimension for the online setting, then we can just learn it by some simple algorithm, for example, empirical risk minimization. And we only need to pay some vanishing generalization error. So there is a huge gap between what we know in reinforcement learning and what we have in supervised learning. And this motivates us to ask the following question, which is also the main question of this talk. What are the minimal structural assumptions that empower sample-efficient reinforcement learning? So here, we really want to go beyond those very special cases and avoid those strong assumptions. We want to discover some mild and general conditions. We want to formalize a really rich class of IO problems that can be efficiently learned. So because we want to do some very general class, in this talk, I will not focus on the computational efficiency. I will only focus on the sample efficiency. So in other words, I want to first solve the statistical problem. And to answer this quite big question, of course, the minimal structure is really difficult to find. But we can still advance our understanding of this question by making the following two steps. So first, we identify a rich class of reinforcement learning problems. And hopefully, this class is rich enough so that it can cover a lot of problems of interest in practice. And second, after identifying this function class, I want to say it is tractable. I want to design some sample-efficient algorithms so that I can learn those problems in this class. And in the remaining of this talk, I will mainly focus on these two steps. Before I introduce our results, I want to briefly mention the previous attempts along this direction. So in addition to linear function approximation, or LQRs, those very special models, there are actually two works that study generic function approximation. One is by Jiang et al. In 2017. So they proposed a class of problems of low Bellman rank. This class includes linear MDPs, tabular MDPs, linear quadratic regulators. It also includes something called reactive poem DPs. So this is basically a special case of poem DPs, where the optimal policy only depends on the current observation and doesn't depend on the history. And they also include reactive PSRs. This is something similar to reactive poem DPs. And another line of work is by Wang et al. In 2020. So they defined a class of problems of low eluded dimension and proved that as long as the problems have low eluded dimension and satisfy certain completeness assumption, then you can learn it using polynomial samples. This class includes LQRs, linear MDPs, tabular MDPs, and additionally includes some generalized linear MDPs. So basically, they can tolerate some nonlinearity in this class. So, but however, if you look at those two papers, the definitions of these two classes look very different. One is saying the Bellman residual has some low-rank structure, and the other one is saying the parametric function class we use has low eluded dimension. And the algorithms they use are also quite different. One uses hypothesis elimination, and the other one uses optimism with sensitive sampling. So the two frameworks have dramatic differences in both the definitions of function class and the algorithm design mechanism. So we are wondering if we can unify them into one framework, and is there some more general class that is efficiently solvable beyond these two works? And it turns out our answer is yes. This is the new class we can define. We introduced a new complexity measure called Bellman Eluder Dimension. And we will prove later the problems of low Bellman Eluder Dimension contain both problems of low Bellman rank and also problems of low Eluder Dimension. So basically, we can see this new class contains almost all the existing tractable reinforcement learning problems. So if we are good, we will move on to the algorithm part. So after defining this rich class of problems, we need to design some sample efficient algorithms for solving them. So specifically, we have two sample efficient algorithms. The first one is new and is proposed in our paper. It's called GORF. So GORF is an optimization-based algorithm using global optimism. As we will see later, this algorithm is surprisingly simple and clean. So basically, I can describe it using only one page. So not only the algorithm itself is simple and clean, its rewrite and sample complexity guarantees are also pretty good. We will see there is a match or improve over the best existing results for several known subclasses. And the second algorithm is an old one.
Yeah, there is one question.
Yeah, sure.
Well, okay, Gerge decided that maybe it's for later, but I think it's good now. Kong was asking, what are the examples not covered under the Bellman Eluder framework?
Oh, so you mean what is an example outside?
Yeah, like is there any MDP that lies outside of your blue thing?
Yeah, I think there are a lot of hard MDPs you cannot learn using polynomial samples. Yeah, I think there are a lot of such hard cases you can construct that lies beyond this class. But I think the key point here is for most of the known examples, for most of the known MDPs, they lie in this class. Because you can always construct some very artificial example that is not learnable efficiently.
I guess the question is more like are there any other sample complexity-wise tractable examples that lie outside of the blue thing bubble?
I think there is one example called Deterministic Translation. So there is some deterministic translation MDP proposed by Ben Van Roy and his student. So I think that case is not included in this big class, but it's still tractable. Yeah, I forgot.
Yeah, it's like the Q star realizability and the deterministic transition.
Yeah, right, exactly. Yeah. Yeah, right.
Okay, so okay, that's cool.
Let's continue. So the second algorithm is an old one. So this is proposed by Jiang et al. In 2017. So it was initially designed to solve the low Bellman rank problems. And it's based on hypothesis elimination. In this paper, we provide a new analysis based on our definition of Bellman Eluder Dimension. And we extend the guarantee of Olive from the original low Bellman rank setting to the more general low Bellman Eluder Dimension setting. I think this is basically all I want to say about the overview. So now let's go to the mathematical part to formally introduce our results. We will adapt the standard setting of reinforcement learning. Specifically, we are going to work with the so-called episodic Markov decision process. And the results for the infinite horizon setting can follow similarly. Here, we have a state set S, an action set A, and a transition measure P, specifying the distribution of the next state conditioning on the current state action pair. And we denote the reward function by this small r, which maps a state action pair to a scalar between 0 and 1. And we denote the length of each episode by this capital H. In this talk, we will consider the exploration setting. By exploration, I mean we don't assume access to some simulator or access to some behavior policy that can guide us to collect samples. And without loss of generality, we assume we always start from a fixed initial state, S1, at the beginning of each episode. In reinforcement learning, we have several frequently used concepts. The first one is policy. So it's basically a map from the state side to the action side. Because we are doing the single agent setting, we only need to consider deterministic policy. And the second one is value function. So it's defined as the expected cumulative reward. So if we start from some state S, we will use the V function. And if we start from some state action pair, we will use the Q function. And the objective of reinforcement learning is to find the optimal policy to maximize the cumulative reward, starting from the initial state at the first step. And it has been proved an optimal policy always exists, and its corresponding optimal Q value function, Q star, always satisfy the so-called Bellman optimality equation. So this Bellman optimality equation says the optimal Q value function, Q star, at step H is equal to the Bellman operator operating on the optimal Q value function at step H plus 1. And of course, this Bellman optimality. Sorry, any question?
Yeah, are we assuming finitely many actions?
No, we don't assume finite actions here.
Can't you just have like some nasty case where the action that gives you maximum reward, no further rewards, doesn't exist? You could, right? Like some assumptions would be needed, but like this is nitpicking. Like moving on. Sorry.
Okay, so we assume the maximum can always be reached. Maybe we can make that assumption. Okay, so of course, this Bellman optimality equation is only satisfied when my value function is Q star. So if I replace my value function, if I replace this Q star with some other function f, it will introduce the so-called Bellman error, which is defined as the function at step H minus the Bellman operator operating on the function at step H plus 1. So in addition to which step H, we compute this Bellman residual. It's also important which function f we use and which distribution rule we pick here, because the Bellman residual is a function over the state action space. In order to obtain a scalar, we need to evaluate on some distribution so that we can obtain some scalar. So there are two things. So I want to emphasize again here. So there are two things important in this Bellman error: the function you pick and the distribution you choose to evaluate your Bellman residual.
So okay, maybe we have a question. I mean, it's still on what is captured by the definition of Bellman Eluder Dimension. For instance, factor and NDPs are covered by this definition.
Factored MDPs. So what do you mean by factor MDP? Do you mean low rank MDPs Sorry, could you clarify?
They will be asking about when, like, you have these little base nets describing the transitions. So it's like the transition dynamics is given in factored form, and then the question is whether you correctly the sample complexity is going to count how many parameters you need to estimate in this factored form, rather than like, if you expand everything in a tabular case, then you would have a combinatory explosion of the number of parameters. But if you knew about this structure, then you can get away with a much smaller sample complexity, right? So I think that that's what the question is going after.
Yeah, I think this is a question about actually. I think actually, yeah, means the factor MDP means like the transition can be factorized into each independent factors, and they have the individual transitions. And I think also to answer, actually, I believe we haven't checked the factor MDP, so it's a very good question. So if factor MDP is not covered in the original Bellman rank, I think so far it's not very clear. We haven't checked it, but it's a very good question. Yeah, we'll probably check it afterwards.
Yeah, I agree. Yeah, if it's not in the low Bellman rank paper, we are not sure about that. Okay, so in this work, we will use value function approximation. We will assume we have a function class f, which is defined as the Cartesian product of the function class at each step. So f1 to f capital H. So each f1 to f capital H defines a function class over the state action space. And we will use this small f without any subscript to define a vector of f1 to f capital H. So this is basically a collection of all the value functions for each step. And we want this function f to be close to the Q star, which is the optimal value function of the MDP. And in function approximation, there are two commonly assumptions. The first one is realizability, which is basically assumed by all prior works. Realizability essentially says our model is not misspecified. The optimal Q value function lies in the given function class. And the second one is completeness. We have two algorithms. One of them requires completeness, and the other one does not. So this is like an optional assumption. But still, the completeness is assumed by a lot of prior works and is necessary for some specific settings. The completeness says after the Bellman operator, my function class is close in some sense. That is, for any function in this fh plus 1, after we apply the Bellman operator, we will obtain some function inside this fh. Question?
Yeah, I have a very quick question. Here is really just about the closeness of the function space. So in other works, if I remember correctly, they assume that any function is basically transformed into a function that is inside the function class that you consider. Here is just really on the function class that you are looking at.
In this paper, we only need to use this weaker assumption. Actually, yeah. So I think you are talking about the paper by Wang et al. In that paper, they need to use a stronger completeness assumption. That is, for any function, after you apply the Bellman operator, you should still be inside this fh.
And that's because if you start to add bonuses, then the bonuses move you outside of the function class?
Yeah, right. Yeah, I think that's the reason why they require the stronger version of completeness. But in our paper, since we are not using that scheme, we can avoid making that strong assumption. We only need to use this standard one.
Okay, thanks.
Maybe I just like save this for later, but you mentioned that you can remove the completeness assumption, but I was wondering whether something else is going to come in
Yeah, right. Well,
like if you already
yeah.
have realizability, that this is not gonna fly.
Yeah, right. So after removing the completeness, we can only do a limited class of our big class. So we cannot do all the problems I described it before. Yeah, it comes at a cost.
Makes sense. Thank you.
Yeah, thanks for the question. Okay. The final thing is the Eluded Dimension. This is like the most technical part. So I will go through it very slowly. So my intuition of Eluded Dimension is it is a generalization of the dimension of linear space. In order to define the Eluded Dimension, we need to first define the independence relation between points. So suppose we have a collection of points, x1 to xn. We say point C is epsilon independent of x1 to xn with respect to this function class f if there exists two functions, f and g, such that their values are very close at x1 to xn, but they are very different at point Z. So we can look at this picture. So there are 4 functions in this picture in different colors. We can see these functions, they are very close at x1 to x4, but they differ dramatically at point Z. So I can just pick the blue function and the green function. And we can see their square difference at x1 to x4 is very small, but they are very different at point Z. So in this case, I can see this point Z is independent of x1 to x4. Okay. And the definition of eluded dimension will depend on 2 things. The first one is the function class f we pick. And the second one is this parameter epsilon. And the eluded dimension is defined as the length of the longest sequence x1 to xn, such that there exists some parameter epsilon prime, no smaller than epsilon. And any point in this sequence is epsilon prime independent of its predecessors. Yeah, you might wonder why do we need this epsilon prime? Why can't we just use epsilon? So the reason for using it is to make sure this dimension is monotonically with respect to this epsilon. Yeah, that's the reason why they introduced this epsilon in the original definition. We can view this eluded dimension as some generalization of the traditional Euclidean dimension. So it's some generalization from linear to nonlinear, and from exact dimension to approximate dimension, because we can tolerate an epsilon here. Now we have basically covered all the necessary background knowledge, and I think it's a good time to introduce our definition of Bellman Eluder Dimension. So starting from the eluded dimension, we need to make 2 minor modifications to derive the Bellman Eluder Dimension. The first one is we need to define the distributional version of eluded dimension. So in the distributional eluded dimension, basically the only thing we do is extending the definition from points to distributions. And so first, instead of saying a point is independent of a sequence of points, we say a distribution is independent of a sequence of distributions. So here everything is the same except that we are evaluating the function on distributions instead of at points. And the other minor difference is we only have 1 function here. We don't have 2 functions as in the original definition. But this is some, negligible difference, because you can recover the original eluded dimension by taking this f to be the original function class f prime minus itself. And you pick all the distributions to be pointwise distribution. In that way, you can recover the original eluded dimension. So this distributional eluded dimension is basically some extension of the original one. Okay. Sorry. And the distributional eluded dimension is almost the same thing. It's the length of the longest distribution sequence, such that each term in this sequence is independent of its predecessors. But there is one key difference, though. In order to utilize this distributional eluded dimension, we need to specify the distribution class capital pi here. So we can imagine, because we require this distribution sequence to be inside this distribution family. Okay, so we can imagine if we choose this pi to contain all the pointwise distribution over SA. This definition kind of go back to the original definition of eluded dimension. But the key point here is we will allow this distribution family pi to be something else that not necessarily contain all the pointwise. And this advantage will become clear after we apply this definition to the reinforcement learning setting. Because we know in the reinforcement learning, we cannot just visit any state action pair we want with probability 1.
I have a quick question.
Sure.
If we don't restrict pi, but we take probably all the probability distributions over the underlying space, is it clear that the Eluder dimension, the new one, is the same as the previous one? So it's always the point masses that generate the longest Eluder sequence, or is there some subtle difference there?
Oh, so if you choose this capital pi to include all possible distributions,
yeah, right?
Yeah, actually, we can have some example showing that this can be much larger than the original.
It can be much larger. That's what I was suspecting. That like.
Yeah, right.
It's just going to be a more.
Yeah, because you have more choices.
Yeah, like right. You have many more things to play with.
Yeah, exactly. Yeah, right.
And you can just like elude gaining information by choosing very bad distributions.
Yeah, that's it. Yeah, we have some example in our paper. So there is some subtle difference. Yeah, you don't want to choose this pi to be too large. If you choose it to be too large, you cannot run this efficiently. Okay. Is there any more question? Okay, I will move on. So after we understand this distributional eluded dimension, to define the Bellman Eluder Dimension becomes very simple. So it's essentially the distributional eluded dimension, but the function class we choose is not the original function class, but it is the Bellman residue of this capital F. So this Bellman residue is defined as the value function at step h minus the Bellman operator operating on the value function at step h plus 1. So this is the distributional eluded dimension on this residual class. And of course, this is only for a single step. And because we are doing reinforcement learning, we need to take the maximum over all time steps. And here, this pi is a collection of distributions over S and A. So each pi h is for the corresponding step. This is the general definition of B dimension. But when we want to derive some theoretical guarantee, we need to specify this distribution class pi. And in this talk, we will have two typical choices of distribution class. One is defined as df. This includes all distributions that can be generated by executing some path. So this path is the greedy policy with respect to some function in this function class. And the second one is d delta. It includes all the point mass distributions over S and A. So it basically includes all the points. And as Chaba suggested, when we use this d delta, we kind of go back to the original eluded dimension. Any question?
Yeah, maybe a very quick question about the max. In the sense, you said it as a standard definition, and I partially agree. But can you have something better, or there it's really necessary taking the worst case over the horizon?
I think in our analysis, we need to pay the worst case. Yeah, I think if you don't take this max, it will at most save you a factor of capital H. I guess it will. So according to our analysis, we cannot save too much by not taking this max.
Yeah, I think eventually we will only pay something, a polynomial in terms of this B dimension. So basically, whether you make it max or make it average, it's more or less just differ by a factor of H. And if you're willing to pay a factor of H, polynomial factor of H, there's really no difference in those two versions.
Yeah, actually, I think we only need to pay an additional H, only linear in H. We don't need to pay too much if we don't take the max.
Okay, maybe I have another very quick question about the typical choice of the distributions. I mean, you said that with the last one, basically you fall down to the previous definition. If I just have a high level look at this definition, it seems a little bit of encompassing the case in which you are really online, so you follow a policy, and the case in which you have probably a generative model where basically the distribution tells you what state action to pick. There is some connection there, or is just to cover the previous case, so the original definition?
So are you asking about the connection between these two choices, or are you asking about?
Yeah, I mean, since you mentioned two examples, it was really just if there is some connection, why you consider these two distribution to the online and if you want generative model setting.
I think Matthew is asking a question of why we want to just do this two distribution instead of others. And I think we could talk more about this offline. I think the short answer would be like we consider those two because those two are mostly naturally come up if you do reinforcement learning. Like the first one is like you execute some policy, so you will have some distribution. Like some other distributions, you can do that, but it's not very natural how you come up with those distributions, like in those reinforcement learning tasks. This is like the short version of the answer.
Okay, thanks.
Okay, finally for this slide, it's more like a comment, but it may be important later that it looks like from the definition as this Eluder dimension on the left would not depend on the MDP, but it actually does depend on the MDP. As like the naming, Bellman expresses that too, but this is an instance, like is the relation between the MDP and the function class and this distribution set, which is kind of like captured here. So it's like an instance-dependent notion, right? Which is interesting. It's like a refinement of the instance-independent stuff that was the Eluder dimension was just like, oh, it's like I have this function class, and regardless of what MDP I'm in, it's gonna give me some result. So maybe there will be some questions related to this, right? Like this raises the question of like how big this can be if I, like, or like for what classes of MDPs, other than just saying that like, oh, for those for which this is bounded, that's where we are good. But I guess like you could say that too, and it's just like a different slicing than the MDP class. It's just like, now we're really talking about like picking some property that is expressing how well a function class fits an MDP, and we're analyzing everything in terms of that, and then we'll see that, okay, like for some algorithms this is a really good fit, but how about all of these other algorithms, and like can we have some matching lower bounds, or I don't know, like it becomes all these delicate questions. But I guess like we'll talk about this. I was just wondering about this.
Yeah, we can talk about these big questions in the technical session.
Yeah, okay, yeah.
Yeah, I think there are a lot of things to say about those questions. Okay, so if we are good with the definition of Bellman Eluder Dimension, we can go to talk about its relation with previous complexity notions. So to begin with, I want to identify its relation with Bellman rank. And as we said, this is proposed by Jiang et al. In 2017. So it's a pretty generic notion. The Bellman rank is defined to be the minimum integer d, so that there exist two vector-valued mappings on phi and posi, so that the Bellman error of function f at step h, evaluated using this policy pi g, can be decomposed as the inner product of phi f and posi g. So this posi g here is the greedy policy with respect to some function g inside this function class. The most important observation here is this decomposition disentangles the policy and the value function, because this blue part only depends on the value function, and this red part only depends on the greedy policy. So this essentially says the Bellman error has some linear factorization structure of dimension d. And here I want to comment that we are talking about the type 1 Bellman rank. So in the original paper, they have some slightly different version of definition. Their action AH is not taken with respect to pi g, but with respect to the greedy policy of function f. So in our paper, we call that original definition type 2 Bellman rank. It turns out both type 1 and type 2 Bellman rank have their own advantages. For example, the type 1 Bellman rank, the type 2 Bellman rank includes this reactive PSR, reactive prime DPs, but the type 1 Bellman rank does not include these two examples. But on the other hand, the type 1 Bellman rank includes the linear MDPs, but the type 2 does not. So when we talk about this low Bellman rank class, we actually mean the union of type 1 and type 2. And in our definition of Bellman Eluder Dimension, we also have type 1 and type 2. Yeah, the name is a little bit long. So essentially, we can deal with both cases. But for simplicity in this talk, I will only focus on the type 1 case. We can show for any problem that has low Bellman rank, it also has low B dimension. So I will just call it B dimension instead of Bellman Eluder Dimension. We show the B dimension with distribution class df, which contains all the Rho-in distributions produced by greedy policies, will always be upper bounded by the Bellman rank multiplied by some logarithmic factor. And this epsilon here is the same as the epsilon used in the definition of B dimension. So this essentially says up to some logarithmic factor, our B dimension is always upper bounded by the Bellman rank. So any problems that have low Bellman rank should also have low B dimension. Okay. The second thing we can say is if the function class has low eluded dimension, for any class inside this low eluded dimension, so for any problem inside this low eluded dimension class, the previous works all made or explicitly satisfy the completeness assumption. So we can say as long as we have completeness, then eluded dimension is always an upper bound for the B dimension if we pick the distribution class to be d delta. That includes all the point mass distribution. So this essentially says any problem has low eluded dimension. It should also has low B dimension. So we already see this picture at the very beginning. It's a summary of what we have so far. So we identify a new question.
Yeah, jumping ahead a little bit, but I have a hard time holding this back. So you have these two distribution choices, and you sometimes switch between the two. Are you going to have a single algorithm that works for both?
Yeah, right. We have a single algorithm. We don't need to.
Awesome.
Yeah, that's the most elegant part. Yeah, thanks for the question. Okay, so we identify this new rich class that contains almost all the existing known tractable reinforcement learning problems. And moreover, in our paper, we further show that our site, this low Bellman Eluder Dimension class, is strictly larger than the class of low Bellman rank problem and the class of low Eluded Dimension. Yeah, if you are interested, you can check our paper. We construct some examples that lie in this big class, but not lie in previous classes. Okay, let me be fast. I think I don't have much time. Okay, so far we have defined a rich class, but if we cannot say this is tractable, then it's meaningless. So we want to design some general algorithms that can run any problems inside this class. Before introducing the golf algorithm, let me make an analog to the UCB algorithm in the most simple multi-unbounded setting. So the algorithm essentially, it iteratively executes the following three steps. So first, we pull the arm optimistically. So by optimistically, I mean we will pull the arm with the highest upper confidence bound. And then we will receive a stochastic reward from the pulled arm. And finally, we will utilize this reward to update our confidence interval. And we know this very simple three-step scheme works pretty well in the multi-unbounded setting. It can give us nearly optimal rewrite and sample capacity guarantees. But it turns out this simple scheme still works pretty well in the much more complicated setting with function approximation. So let me introduce our algorithm on golf. So the first step is still optimistic planning. We still maintain a confidence set denoted as B here. In this step, we will iterate over all the functions in this confidence set and pick the one that has the largest value at the initial state. And the policy we will execute is simply the greedy policy induced by this FK. And in the second step, I will just execute this PyK and collect a new trajectory. And in the final step, I will utilize my dataset to update my confidence set, this capital B. So the most important thing here is how to construct this confidence set. I will talk about this in the next slides.
So maybe I have a question about the optimistic planning. Just to understand the notation, it seems that there is no connection with the next stage.
Yeah, right. That's
yeah. So, that's in which sense planning? Where is the connection with the next next stage?
Yeah, that connection will be. I mean, it will be realized in this confidence set. Basically, we construct a lot of local confidence sets that links every local steps together. Yeah, that's why we only need to be optimistic in the first step.
Okay, thanks.
Okay. So, and the policy we output is simply is uniformly sampled from all the policies we have executed in the previous episodes. So the key idea here is, yeah, just as Matteo asked, is global optimism with local confidence set. This is why we call this algorithm global optimism based on local fitting. So the reason for calling it global optimism is also in reinforcement learning, we have strong correlations between different time steps. Here, we only need to be optimistic as an initial step. We are not computing some optimistic estimate for each step and passing it forward as previous works have done. And for the later steps, we will constrain them using a sequence of local confidence sets. And each local confidence set will only depend on two consecutive steps. That's why we call it local confidence sets. Okay, so our confidence set is the intersection of capital H local confidence sets. For the confidence set at step H, we define it to be all the functions satisfying this condition. So let's parse this condition bit by bit. So this LD is like an empirical proxy to the Bellman error of function f at step H. It's defined as the square loss over all the transition tuples we have corrected so far at this step. And this term is like the ERM of fitting the Bellman operator operating on fh plus 1. So we can also understand it as if, like if we fix the value function fh plus 1 and throw away fh, what function g we should pick to minimize this empirical proxy to the Bellman error. Okay. But the confidence set we construct here is saying we are not gonna directly minimize this empirical loss. We will relax it to allow any function that has a comparable loss to the empirical minimizer. And the degree of this relaxation is controlled by this parameter beta. So the reason for doing this relaxation is we want to keep the Q star function inside this confidence set so that we can use optimism.
Maybe a quick question about this step. Here you're able to build the confidence set based on relative performance because you have realizability. Or is independent from that step?
I think this confidence set. So this confidence set needs to utilize completeness. I think realizability is basically required by all papers in function approximation. But in this confidence set, the assumption we use is, we use both completeness and realizability when we analyze this confidence set. Okay, so go ahead.
So if you wouldn't have realizability and their completeness, errors would blow up exponentially with the horizon?
So if I don't have sorry, are you saying completeness or realizability?
You choose. You choose.
Oh, okay, so sorry,
my question, but yeah.
Yeah, sorry, my earphone has some echo, so sometimes I cannot hear it clearly. So if you're asking about realizability, then if we don't have realizability, this confidence set may be empty. So we don't want some empty confidence sets. And if we don't have completeness, they say, yeah, I don't know how to obtain some meaningful guarantee from this construction because this construction heavily relies on the completeness assumption. It's like because when we have completeness, we can say as long as the function satisfies this inequality, it should be close to the Bellman operator operating on fh plus 1. So that's something we want. If we don't have completeness, we cannot obtain something like that.
So regarding the first realizability, if you had misspecification but you knew the misspecification error, you could add an extra term.
Yeah, right.
Right?
Yeah,
right. Yeah, like would that fix the problem or that still causes other problems?
So if the misspecification error is not so large, I mean, yeah, if it's large, it can also be very large. So if we want to do some misspecification error, we will obtain an extra term in our final result. It's like h squared times the misspecification error. So basically, we need to pay some additional error linear in that thing.
Sure, like that's fine.
Yeah, we can do that, I think.
Can ask the question, okay, what if you don't know the misspecification error level, but then can you adapt to it? But this is good. At least you can deal with some basic level of misspecification. Completeness is still a question.
Yeah, I think completeness is really required, at least by this algorithm. So we have the following guarantees for our algorithm GORF. So assume realizability and completeness. GORF can find an epsilon optimum policy within this number of episodes. So here, H is the length of each episode, and D is the Bellman Eluder Dimension with respect to either D delta or DF. Yeah, you can pick the smaller one. And this NF is the covering number of this function class with respect to the infinite norm. So if the function class is finite, this NF is always upper bounded by its cardinality. And moreover, we also have some regret guarantee. This regret scales as square root of the number of iterations, capital K, the B dimension D, and the log covering number of function class this function class capital F. So the most important thing here is GORF can learn any low B dimension problems sample efficiently under these two assumptions. So we don't need to design different algorithms for different problems in our class. We have a universal algorithms that works for all of them. Yeah.
Wait, so what's pi here? Oh, pi is the minimum. Okay, good. Yeah.
Okay. Yeah, and actually, okay. Yeah, I can see that later. Yeah, let me finish the main results first. Okay. And to show the sharpness of our results, we specialize the sample capacity and regret guarantees to the following subclasses. So in linear function approximation setting, we have regret D times root K. So D is the dimension of the linear function class. So this matches the optimal regret in the net et al. In 2020. And in the low eluded dimension setting, we have regret scaling as the square root of the eluded dimension times the log covering number and times the number of iterations, capital K. So this improves over the result in Wang et al. By a square root of the eluded dimension. And actually, I think their result also depends on the log covering number of the state action space. And they also adopt a stronger version of completeness assumption. And so in comparison, our results don't depend on the state action space and only requires the standard completeness assumption. And finally, for the low Bellman rank setting, our sample capacity scales linearly with respect to the Bellman rank. This improves over the square dependence in Jiang et al. 2017. However, we achieve this improvement at the cost of assuming completeness, which is not required in their paper. So this raises our final question. So can we design something that works without completeness? And the answer is yes. It turns out we can reanalyze the Olive algorithm. This Olive algorithm is based on hypothesis elimination and is proposed in Jiang et al. In 2017. Because the algorithm is a little bit complicated, I will skip the description here and only introduce its theoretical guarantees. So for this Olive algorithm, we only need to assume realizability. We don't need the completeness assumption. So we prove Olive can find an epsilon optimum policy within this number of episodes, and this D is the B dimension, and NF is the log covering number. So here we have square dependence on the B dimension, and we can only deal with the B dimension with respect to DF. We can no longer do D delta. Okay, so compared to Golf, it has a worse sample capacity. It cannot do D delta. It has no regret guarantees, but it doesn't require completeness. So I would say these two algorithms are not directly comparable with each other. Okay, finally, let me make a brief summary of this talk. So first, we identify a rich class. It basically contains all the existing tractable problems. And we have a new sample efficient algorithm, Golf, that can solve these problems of low B dimension. It is simple, it is clean, and it has a sharp rate. And we also have a new analysis for Olive. Previously, it's only proved to work for a subclass. And now our proof extends the guarantee to a more general class. And if you look at our paper, the proof is very simple. Basically, it only uses the definition of B dimension. It can be written using like half a page. Okay, so I think that's it for today's talk. Thank you all for coming.
Yay.
Hey, thank you.
Yeah.
So maybe I can go with a question, I guess, standard on the algorithm itself. What is the computational complexity? It is efficient to I mean, we can solve it.
Yeah, I think our algorithm is not computationally efficient. Yeah, because as you say, I mean, both algorithms are not computationally efficient. So in this optimistic planning step, we need to iterate over all functions. So this is not efficient. And we need to maintain this confidence set. It's also, I mean, it's also not efficient. And for algorithm Olive, I think those authors also have another paper showing that in the worst case, Olive is also NP-hard, I think. By actually Jiang et al. I think also, yeah, and the Princeton, yeah, I think. Yeah, yeah, so in short, both algorithms are not efficient in general.
Okay, thanks. We have also a question by Gerg about the algorithm. So if we consider the case h is equal to 1, so only one stage, is it equivalent to the UCB algorithm of Rosen-Barrois?
I think if are you asking about contextual? Oh, so in this, so in our setting, we assume the initial state is fixed. So it's essentially a multi-unboundedness. It's a multi-unboundedness problem. And in that case, I think our algorithm will degenerate to the UCB algorithm I mentioned here, because you only have one state, and if you choose the function class to include all the possible functions, then it will degenerate to the UCB algorithm here. But if you choose the function class to be something else, for example, if your function class is very small, then you don't need to pay the number of actions. You only need to pay the cost, the complexity of this function class.
Right, but I pretty much meant the case when you have a random first state, which is like the contextual bandit problem. So for IID contexts, is it really the same as the algorithm in the Eluded Dimension paper? Can you comment on that?
So you're saying you mean the contextual bandits problem? I would say if the so if h equals to 1, I think our results can also apply to the contextual bandits problem. I think it will kind of recover the result in the original Eluded Dimension paper.
Yeah, that's for sure. No, I was just wondering if this algorithm becomes exactly the same algorithm as in that paper, if you consider this case.
I think it will.
Because their confidence set has a very similar shape, right?
I think it's slightly different because if you go back to the if we go back here and look at this definition of Bellman Eluder Dimension. So actually we are looking at the Bellman residual. So if the horizon is equal to 1, this function class will be all the functions in this class minus the true reward function. So that's something slightly different. So in other words, you can think of so yeah, in other words, you can think of it as some, so it's a function class smaller than the original Eluded Dimension class, considered in the original Eluded Dimension paper. So we can show there exists some example. Their guarantee can be much worse than our guarantee. So even
Greg's question is the algorithm. I believe the algorithm is more or less the same, isn't it?
The algorithm is the same, but the guarantee is different. The guarantee is different.
The guarantee is slightly different. I think in the definition of set is a little bit different. Yeah, but I think it's also not that big difference, I feel. Anyway.
Right. But basically the shape of the confidence set it seems to be very directly inspired what their confidence set is in that paper.
Yeah. In the bandits case, it looks similar.
Right. Okay, thank you.
And no problem.
I had a, I don't know, slightly provocative question. I don't know. It's not meant to be provocative, but it's just that we had this algorithm, UCRA VTR. I don't know. Whether you have seen the paper? It's model-based reinforcement learning with value-targeted regression. So it's kind of like a different ballpark of algorithms because this is about model-based RL. But that's also pretty general. I don't think that we need completeness or anything like that. The Eluded Dimension is used in connection to the models in some not so necessarily too simple way to get the analysis going. It covers a bunch of cases, but not these cases. And so I was wondering, like, have you thought about whether are these complementary completely, or like is there a big unification of these things somewhere? it seems that at the moment they are going in quite different directions, right? So the problems covered by that paper are not going to be covered by this paper, and vice versa, which is like, wow, I don't want that. I want one algorithm that does everything.
Yeah, I also want the same thing. Actually, I thought about that when writing this paper. I read your paper, but I can't find a good way to unify both things. So
Yeah.
I just stick to our original thoughts.
Yeah. It's awesome. I was trying to go the other direction, and I was just thinking,
I think that's a pretty good. Yeah, that's a fantastic paper. Yeah, so it's just we are going along different directions. I think your paper is more like model-based things, and this one is more value-based.
But does it have to be like that? Like we are separating these words where these distinctions are like somewhat hypothetical anyways, and like, it's kind of interesting.
Yeah, right. Yeah. I also hope one day there could be another paper that unify all of these things. Yeah. That would be super great.
Right. Inevitable question, lower bounds.
Oh, lower bounds. I think under the current framework, so without making further assumptions, I think this rewrite is something almost optimal we can achieve, because our setting includes the linear function approximation setting, and I think in the next paper they show this rate is basically optimal. So if they cannot do better than this rate in the linear setting, I think we can also not do better than that rate in our setting. Yeah, because if you
I'm wondering whether there is a finer
dependence on H.
Yeah, finer. No, not finer dependence on these quantities. But yeah. So, right. So you take all the MDPs whose Bellman Eluder Dimension is right. So you want to have a lower bound which works like this. I give you any function class. Oh, okay, like if I make it any function class and not fixed, like not a subset, then you will include the linear functions, and then
right.
This lower bound applies. But when I say that I want something finer, I want like that. It's just like somehow like if we fix the function class in some way, but it's not the linear guys. I guess I don't have a very good question here. I have to think about it.
Yeah. Well, I guess your question, Java, is that, well, is the notion of independence that is being used in the Eluded Dimension, is this somehow correct, or is this like capturing really like a good definition of independence for general function classes?
Maybe
that's a different question.
Yeah, honestly speaking, I'm not sure, because there are not so much complexity notions in reinforcement learning. Because maybe there are some other complexity notions.
Right.
That we can use beyond this eluded dimension. Maybe we can
so you can come up with examples, like artificial examples, where like you're learning about the function, the identity of a function, and you can get away with many fewer samples than what the Eluder dimension for that function class is. So it's Eluder dimension is worst case optimal in some cases, but it's not going to be like in every case capturing whether you can adapt to some other structure in the function class. And I guess like if you're building on Eluded dimension, then this property is going to be inherited. Yeah, like that's a valid question of whether there is any refinement of these, which would for which you would be able to get the same type of guarantees, and which would be smaller, like uniformly dominating this.
Yeah, I agree. This Eluded dimension is the worst case guarantee.
Yeah.
I think that's what. Okay. Yeah, I agree.
And if I may, a little bit into this direction, is again going toward the dimension of the distribution that you consider. You know, the two one that you are considering seems to be reasonable given the result that you get, but it seems that you have an additional freedom there, and will be interesting if it's possible to design even a better distribution or consider different distribution and get something out of it.
Yeah, I think this is a great suggestion. Yeah, we have been considering this for a long time. So yeah, we want to know what we can do beyond these two distribution families. Yeah, what we can do else? Can we make things better? So I think this is a great question, and it's also a good future direction. So it will be super great if we can find some other implementable distribution family, so that this B dimension is relatively small. Yeah, and that would be super great. I think this is a great question. Yeah, we definitely should try to see what other function class, what other distribution family class we can do. I think that would be super great.
Yeah, Gabor, go ahead with your question. Thanks.
Yeah,
hi. So the question is, do you need to take the uniform distribution to output the policy and golf, or can you just pick the last one? So why is it necessary?
Because
I guess I can answer that very fast. I think the answer is basically we just do a very simple trick as a like online to batch conversion. So we say we have to uniform output policy. And if you want to last trick guarantee, I think it's doable if you kind of like adding some techniques like to check like whether you're doing multiple improvements or something like that, and and do some like open box analysis instead of like just directly doing this online to batch conversion. We do some further analysis. It's just doable, but it's kind of like we're too late.
Maybe, yeah, like that's the planning setting, right? So you could just like take all the policies and run through the simulator and then choose the best.
Yeah. Right.
It's not really a last iterate guarantee. The last iterate guarantee would be cool to have, but for that you definitely
you don't need the simulator, right? I think.
Oh yeah, you can run with the real world if you want.
Yeah.
But I mean, like I call this a planning setting because I don't know why.
I think the tabular setting. I think Princeton or Zenat they have some paper like they can essentially construct a certificate for each policy and say like the performance of policy is lower bounded by something. So basically, you not only have upper bound but also have lower bounds. And this way will kind of tells you whether like the policy you run in the episode case is good or not. And so eventually,
I feel things are a little bit different because if we maintain some upper confidence bound and lower confidence bound, we cannot control the Bellman error in the later steps. So I think only
you knew that. like you just run these policies for not too many samples, estimate the return from the initial state, use Hovding's inequality, and be happy with that.
But in that case, we cannot obtain like 1 over epsilon square, I think.
What?
Are you sure? Like, of course you
No,
can.
I think there are a lot of ways to do that. I think one thing I can think about is like, as Chaba said, I can use some number of samples to just evaluate one policy, and we only need to evaluate the like logarithmic number of policies to do some boosting type of arguments. Because so far we have constant probability our policy is correct.
I think in that way we can still not do last iterate guarantee.
You'll probably not last iterate, but basically guarantees the output I have, the policy. And the policy I have will be good with high probability. So
I agree. I agree. Yeah, that's true.
Yeah, you just have a few policies that you need to choose from, so that shouldn't be a problem, right?
Yeah, that's true. That's true.
But maybe the last iterate, I'm with Beachy on this. The last iterate guarantee would be really nice.
Yeah, but then the conclusion is just so this is just simplifies the analysis, and if you don't have an efficient algorithm, then it doesn't matter much.
Yeah. Good to see you.